Hello everyone, I'm Jie Yang. For final project paper review, I prepared two papers from Variational Inference and PC Fairness. The first paper I'm going to present is Efficient Variational Inference for Sparse Deep Learning with Theoretical Guarantee. Sparse deep learning is used to compress deep learning model for hardware-limited devices or recover potential sparsity structure of the target function or variational selection. Previous work about pruning method has no theoretical guarantee on choosing the threshold. Another work for sparse deep learning with theoretical approach cannot be implemented in efficient way. To overcome this limitation, this work covers complete package of both theory and computation for sparse deep neural network using Bayesian perspective. Let me briefly introduce about background of variational inference. Bayesian procedure makes statistical inferences from the posterior distribution. Since MCMC does not scale well on complex Bayesian learning tasks with large data sets, variational inference has become popular alternative. Variational inference approximates the true posterior distribution by finding a closest member in terms of KL divergence. The variational inference procedure minimizes the reconstruction error while being penalized against prior distribution in the sense of KL divergence. In this work, they aim to approximate underlying true function f0 in the generated model by a sparse neural network. For this, they consider a non-parametric regression model with random covariates. Sparse neural network can be represented like this way. P means the width of the network, and L is the total number of hidden layers, and S is the number of non-zero edges, where theta means all the coefficients in the neural network. From a Bayesian perspective, we impose a spike and slap prior on theta to model sparse DNN. A spike and slap distribution is mixture of two components, a direct spike concentrated at 0 and a flat slap distribution. Spike component and slap component represent whether the corresponding edge is inactive or active respectively. This work distinguished itself from prior works on Bayesian sparse neural network by imposing the spike and slap prior with the direct spike function. Hence, automatically, all posterior samples are from exact sparse DNN models. Now let's look at main theorem part. This work defines S star, the optimal S, that strikes the balance between the variational error and the approximation error. Interestingly, we do not need to find S star, as this modeling attains the same rate of convergence as if the optimal S star is known. The main theorem is about the contraction rate of the variational distribution. It is bounded by three error terms: estimation error, variational error, and approximation error. These three errors are all functions of S star, L, N, which is already model parameter. The complete variational inference procedure with Gumbel softmax approximation is stated in the algorithm 1. Gumbel softmax is used to reparameterize the discrete variable by a continuous system via stochastic gradient optimization. This exploratory studies demonstrates little differences between the results of using inverse CDF reparameterization and using Gumbel softmax approximation in some simple model. Therefore, this work conjectured that Gumbel softmax approximation does not hurt the VB convergence and thus will be implemented in numerical studies. This is the experiment results. This work considers two teacher network settings for densely connected, and network parameter is randomly sampled from uniform distribution. And second one is sparsely connected with fixed network parameter. This figure shows that an overly small lambda leads to overspecified DNNs with insufficient expressive power, and an overly large lambda leads to overfitting DNNs. Similar to the teacher network simulation, they study the impact of lambda and results in figure. This figure justifies that optimized lambda is reasonable choice. In addition, proposed method achieves smallest FPR and acceptable FNR for input variable selection, while other methods select huge number of false input variables. Lastly, they evaluate the performance of this method on MNIST data for classification tasks by comparing with benchmark results. A two hidden layer DNN with 512 neurons in each layer is used. They compare the testing accuracy of proposed method with optimized lambda to the benchmark methods at different epochs using the same batch size. The graph shows proposed method achieves best accuracy as epoch increases with high sparsity level. In conclusion, this work proposed a variational inference method for deep neural networks under spike and slab priors with theoretical guarantees. Future direction could be investigating the theory behind choosing hyperparameters via EB estimation instead of deterministic choices. Furthermore, extending the current result to more complicated networks is not trivial. The second paper is about PC fairness, a unified framework for measuring causality-based fairness. Some figures in the slides are from the author's conference poster. Fair machine learning is now an important research field which studies how to develop predictive machine learning models such that decisions made with their assistance fairly treat all groups of people, irrespective of their protected attributes such as gender, race, or other things. One common challenge of all causality-based fairness notions is identifiability, called whether they can be uniquely measured from observational data. In addition, it is not clear whether previous work can be applied to other unidentifiable situations, and more importantly, a combination of multiple unidentifiable situations. To alleviate this problem, they define a unified fairness notion that covers most previous causality-based fairness notions, namely path-specific counterfactual fairness, also called PC fairness. To this end, they develop constraint optimization-based approach for tightly bounding and unidentifiable PC fairness. First, I will briefly explain the background of causal inference with the notation that paper used. Causal effects are responses of the outcome of interest to external intervention. Quantitatively measuring causal effects in causal model is facilitated with the do operator, which forces some variable to take certain value. By using do operator, the total causal effect is defined as follows. The total causal effect is defined as the effect of X on Y, where the intervention is transferred along all causal from X to Y. If we force the intervention to be transferred only along a subset of all causal paths from X to Y, the causal effect is then called the path-specific effect, defined as follows. If we have certain observations about a subset of attributes and use them as conditions when inferring the causal effect, the causal inference problem becomes a counterfactual inference problem. Next, I will explain background for causal fairness learning. The green path effect is considered as explainable. The red path is considered as indirect discrimination. The purple path is considered as direct discrimination. Counterfactual fairness is the total effect for a group specified by the factual observation. The blue box denotes the real factual world. The purple box denotes the counterfactual world. Green represents the condition and yellow is the counterfactual quantity. Path-specific counterfactual effect of X on Y for a given condition O through a path set pi is given like this. Thanks to the flexibility and capability of the path-specific counterfactual effect, the PC fairness generalized the previous causality-based fairness notions. The key barrier in PC fairness is the unidentifiable issues. Examples of typical unidentifiable situations are shown through figure 2, 3, and 4. They formulate the bounding problem of PC fairness as a constraint problem by using response function variables. Response function variables are used to parameterize the causal model. Categorize the unknown domain of U into limited number of equivalent regions, each of which is denoted by a value of response function variable. Represent unknown functions f by a limited number of mappings from parents to dependent variables. Each corresponds to one equivalent region of U. As a result, all uncertainties in the causal model parameterized PR. Based on the response function variables, finding the bounds of PC fairness is formulated as follows. Objective function is the path-specific counterfactual effect. PV is the parameterized distribution which agrees with the observational distribution PD. This is the experiment result. The causal model consists of 4 endogenous variables, and they consider 2 versions of the causal mode. The distribution of exogenous variables and structure equations of endogenous variables are randomly assigned. Finally, they generate 2 datasets from each version of causal model. The first column in table 2 indicates the indices of O's value combinations. The true value of PCE fall into the range of our bounds for all value combinations of O, which validate proposed method. Table 3 shows that proposed method achieves much tighter bounds than previous method, which can be used to examine fairness more accurately. In this paper, we propose a general framework for measuring causality-based fairness. For this, we formulate a linear programming problem to bound PC fairness, which can produce the tightest possible bounds. As a result, our method can bound causal effects under any unidentifiable situation. The future work can be done with concern of scalability. First, they noticed that not all response variables are needed in the formulation, and only those that directly lead to an identification are needed. As a result, the total complexity of the problem formulation could be significantly reduced. Also, how to construct fair predictive models based on the derived bounds is another future research direction. This is the end of this presentation, and thank you for listening.